Okay. So we continue with the example number Q3. And solve the following using ranking theory. Okay. So draw the distribution of active pressure and calculate the total thrust behind the wall as well as the location of the line of action. Okay. So we need to determine the total thrust and also the line of action. Okay. B, draw the distribution of passive pressure and calculate the total thrust in front of the wall as well as the location, the line of action. Okay. So for the active, okay, and also for the passive. So we look on the diagram. So So, similar approach, where we need to what we call as the initial distribution, initial pressure, any changes of the soft properties, and at the end of the retaining wall structure. Okay. So, behind the wall, okay, consider as an active. Okay, get the KA for the first layer and KA for the soil sector. See? So let Z equal at the backfill surface. Okay? So sigma V equal to 30, okay, due to the surcharge. We then put the sigma V in the equations. Okay, we multiply with the active coefficient of active minus with the 2 times square root Ka. Okay. From there, sigma A is equal to negative 20.83. Okay. So at the depth of 3 meters, okay, the same approach, active, vertical effective stress 85.5. So since there are changes in soil strength parameter C and Phi, so we need to consider the active pressure at points slightly above and slightly below this 3 meter level. Okay. So the same approach as before, okay, sigma A 18.24 for the slightly above, for the slightly below 28.5. Okay. At the Z equal to 5 meter, sigma V is equal to 10.5. Okay. Then the active effective horizontal stress is equal to 35.17. Okay. So for water pressure is to 0 from that is at 3 meter. At 5 meter, the pore water pressure is equal to 10 times 2. Okay, as I mentioned before, we use unit weight for this example as 10 instead of 9.8. Then we plot the active distribution diagram, pressure. So use the circular triangle concept. The Y, the area of the Y, sorry, calculate the area of A1, A2, A3, and AU. So the Y is equal to 1.4. Okay. So then the total truss area for A1, A2, A3, and AU is equal to 96.44. Okay. We need to determine the line of actions of the resultant truss. Okay. The total of okay, is equal to 1.1. Okay. So that is for the active part or active area. Okay, then for B, okay. So for the passive part, the equation is the effective horizontal pressure at passive slip is equal to sigma V Kp plus 2C square root Kp. So then the Kp is equal to tangent square 45 plus P over 2. For the K surface of 10. Okay. So get what is the passive lateral force, which is equal to 30 at the depth of 1 meter. Effective 28. Okay. Then determine what we call as the passive lateral stress, and we obtain 84. Okay. So the total acting on one face of the wall can be obtained by adding together area AP1 and AP2. Okay, then PP is equal to 57. Okay. So the last one, the line of actions, plus total moment of area figure 13B. Base of the wall is divided area. Okay, so from there, Y average, we obtain 0.42 above the base of the wall. Okay, so that is for the example Q3. Okay, for this example, we include the passive value as well. Okay, the Q2 only on the active, Q1 discuss on at rest. Okay, any question for the example number Q3? Okay. No question? So then I can proceed for the Q4. Huh? Ada? Is there
Sir,
any question? Martin.
yes. So for the active
Betul.
side, we don't consider the negative force scan.
Yes, yes.
Yes, yeah. But if in the passive side, say for example, there's a apa?
Negative.
Yeah, if there's a negative force spoon, we don't also consider that, right?
Yes, yes.
Yes. Okay.
Because we assume, yeah, it is a like, yeah, for the passive, we assume the soil for the soil for the passive.
Move.
Siapa tu?
Okay.
Sorry,
Okay.
ada dengar suara lain?
Ah, sorry. That's my family.
Oh, okay, 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 okay.
Okay. Okay.
Okay, Martin.
Sorry.
Okay,
Sorry. Yeah.
okay. Both of the case, we only okay,
Positive side. Okay. All right.
because the positive side for the active, it represent the expansion, while positive side for the passive, it represent the compressions. Okay,
Ah. Okay. All right.
passive, the positive is compression, while for the active, positive is the expansion. Okay, but negative is the compression, and for the passive, the negative is considered as the expansion. Okay, so it differentiate based on the either active or passive. That's why we only consider the positive side only.
Okay, sir.
All right. Okay. So no question on Q3, yeah? Okay. So now we move to the Q4. Okay. So this Q4, okay, we deal with a sheet pile, okay, and then we need to determine what is the load T to be carried by each anchor. Okay, if the horizontal spacing between anchor is 2 meters. Okay, so I need to sketch first and to show the situations. Okay, so let's say this is your sheet pile. So then let's say this is the anchoring system. Okay. So means that the distance between one anchor to the next anchor, okay, is to the okay. So that is the spacing one anchor to another anchor. Okay. So means that for every 2 meter there is an anchoring system. Okay. So means that for every 1 meter, okay, we need to divide the loads or the tensions on the anchor into half, because for every 1 meter, it contribute half of the tensions on the anchoring systems. Okay. Let's say if if the spacing is 1 meter, okay, so means that for every 1 meter, okay, we divide into one, so means that it represents per meter run. Okay. How about if the spacing is 0.5? Okay. For this case, for every 1 meter, we need to multiply with 2. Okay. Because the spacing is 0.5. So means that for every 1 meter, we need to multiply with 2. Okay. So that is how we deal with the anchoring system. Okay. So if 2 means that for every 2 meter, we install the anchor. Okay. On how to calculate the capacity of the anchor. So for every 1 meter, we need to divide with 2. Okay. So now we look on the calculations. Okay. The material, okay. The material behind the wall are sand underlain by clay sand. Okay. There is a uniformly distributed load on the backfill. Okay. So we look on the diagram. Okay. So this is the arrangement of the anchor and the sheet pile, okay, to stabilize the soil, okay, at the back of the sheet pile. Okay. So we need to know how much tension stress or tensions uh, stress should be applied, okay, to stabilize the sheet pile. Okay. So the groundwater level, okay, on the both side is at the same height. Okay. So on the left side, okay, uh, the ground level is considered at the bridge line. Okay, looks like the sheet pile is construct, okay, as a wall, okay, especially nearby the river. Okay, or it also can become as a wall, okay, quay wall, okay, for the harbor constructions. Okay, for the harbor, they call as a quay wall. Okay, so then we have both sides, okay, of the water is on level. Later on, we can eliminate the pour water pressure because the water is similar at the both sides. Okay. Okay. Use Rankin active pressure approach to calculate the lateral stress behind and in front of the wall. Okay. So the active pressure are acting behind the wall. Okay. So then we use the active pressure equations. Okay. Sigma V Ka minus 2C square root Ka. Okay. Then the Ka tangent square times 45 minus P over 2. Or if you are not memorized the equation, and there will be another equation that you can use, okay, which is 1 minus sin P over 1 minus 1 plus sin phi. Okay. Okay. So note there are layers of the soil with different parameters. Okay. So phi 32, phi 30, where the Ka is 0.300, Ka 0.333. Okay. For the second layer, the third layer is 28, where the Ka is equal to 0.361. Okay. So we have 3 layers of different soil properties. Okay. The first soil have 2 different properties, and the last layer, okay, since it is fully saturated, so it only have single properties of soil. Okay. So then, as usual, we determine at 0 for the initial level 0.5 at 4.5. Sorry. Okay, at 4.5, and the last one it's okay. So we have 4 different levels that need to be considered for the active. Okay. Meanwhile, for the passive, okay, we need to determine the first at 6 meter depth and 8 meter for the next points. Okay. Okay. Let z is equal to 0 at the backfield surface. Okay. Sigma V30, sigma A is equal to sigma VKA minus 2C square root KA. So then we obtain 9.21. Okay, at the Z is equal to 2.5. Sigma V is equal to gamma, sigma V is equal to 72.5. Okay, for the vertical effective stress. Okay, since there are changes in the soil strength parameter, we need to consider the active pressure at points slightly above and slightly below this 2 meter level. Okay. Slightly above this level, sigma A is equal to sigma VKA minus 2C square root KA. Then the value is 22.26. Slightly below, okay, is equal to 24.17. Okay, so that is for the at 2.5 meter. Then we go for the 4.5 meter. Okay, 89.5 is the effective vertical stress above and slightly below. Okay, so for slightly above 29.83 and for slightly below is 20.29. Okay. So at the depth of 7 meter, sigma V is equal to 122.75. Sigma A is equal to 30.3. Okay. Okay. It's not necessary to calculate the pore water pressure behind and in front of the wall, as they cancel each other because it is it located at the same height. Okay. Okay. So in front of the wall, Kp is equal to tangent square 45 plus 5/2. So then we obtain the Kp 2.77. So at the level of the dash line, okay, see, we not consider the pore water pressure. Okay, so then the sigma V is equal to 0. Then sigma P for the passive at the dash line is equal to 33.3. Okay, 2 meter below the dash line. Okay, it's 19 for the sigma V. Okay, and then for the sigma P is equal to 85.92. Okay. So that is for the passive part. Okay. So the stress distributions shown in figure Q1 4A. Okay. So when we deal with a lot of area of pressure, so it's better to put a table. Okay. So for example, for table Q14, okay, so we have 6 what we call as the active fluids value, okay, and 2 to calculate for the active fluids value. Okay. So then we calculate for the first area, continue with the second, okay, and so for the passive, okay, we only calculate for the 2 area only. Okay. So once we obtain the value for the active and passive, okay, so then we put in these equations. So it means that on the active or on the right side, okay, the active minus with half T, as I mentioned before, because the spacing is 2 meter. So for every 1 meter run, we divide it into 2, okay, equal to 119.22. So then the T is equal to 132.32. Okay, so that for the tensions or the anchor. Okay, so the value is 132.32. Okay, any question? Is there any question? Last example. Okay, so you understand. Okay, let's say for your, okay, I give you a similar example for the calculation. Okay, is it okay? It's very straightforward and easy to understand.
Sir, the
Yes.
TNA, is it the two of the anchor or one of the anchor or both of them actually? This T
What do you
value.
what? The T value is for
Yeah,
each
the
anchor.
each anchor.
Uh,
Oh, each
because
anchor.
in this case the spacing is 2 meter.
Yeah,
Okay.
spacing is 2 meter. Yep.
So in order to have a per meter run, okay, so then we divide it into 2.
Oh,
Then
okay.
we need to apply 132.32, okay, to strengthen the anchor in order to stabilize the ship pile.
Okay.
Okay,
So, say
so means
example,
that,
if the spacing between both these anchors, say example, is like 4, right, 4 meter,
okay,
then your the value of the calculation should be what, T over 4?
T over 4. Uh,
T over 4.
uh,
And then if it's 0.5 meter spacing, then it's 2T then,
yeah, multiply with 2.
multiplied by 2. Okay.
It should be based on the per meter run. Okay,
Okay,
however,
sir.
it
Yeah,
depends.
understand.
It depends on the moment, bending moment of the ship part. Okay? We cannot. We cannot uh, have a spacing. Uh, yeah, for example, to save the cost, okay, we use a larger spacing. Okay. At the same time, we need to calculate what is the capacity of the ship pile. Okay. So it should be uh, it should design together. I mean, the anchor spacing and the sheet pile uh, capacity, okay, is related. Okay, so we need to consider the bending moment of the sheet pile. Okay, not only consider the space. Yeah, there where the spacing uh, shall influence the bending moment of the sheet pile. Okay. All right. So this is example to show you if we have a certain spacing, okay, how to define uh, the spacing in per meter run. Okay. I'm not sure what is the maximum spacing. Usually for beam, yeah, use the same concept with the beam. I mean beam in the structure, because we count for the uniform distributed load. From there, we can get the shear force and also the bending moment for the sheet pile. If from there, we need to find what is the maximum spacing or the optimum spacing that we can use to save the cost okay, on the designs. Okay. Got no question, eh? Because actually it's more easy to understand the calculations rather than the derivation of the equations. Okay. So this will be the last, okay, for the what we call as for the C and fee. Okay. But for this case, we use the another approach, another theory. They call it as a column theory. Okay. The one that we use before is based on the ranking theory. Okay. Because for the column theory, they consider the frictions between the wall and the soil. Okay. So later on, we will learn on the frictions between the wall and the soil. Okay. So considering, we look on the figure. Okay. So this is the what we call the figure for a wall. Okay, that has better angle. Okay, and there is a slope on the backfill, and the wall is considered as a rough, okay, rather than smooth. Okay. So actually on our next discussions, okay, we will look on how the derivation work to get the KA. But if I'm not mistaken, the equation is different, okay, as what we will learn later on. Okay. But this is equation based on the column. Okay. In this equation, okay, the column use what we call the frictions between the wall and the soil. Okay. The angle of the retaining structure. Okay. And the angle of the slope. Okay. Okay, since we did only one type of soil, okay, so then we can use this single equation. Okay, we call this a single type of soil. Okay. So how these equations obtain? Okay. So let's say this is what we call as the distributions pressure diagrams. Okay. So then this is the height. Okay. So for the effective horizontal stress, which is the gamma times h, it actually represents the vertical effective stress times with Ka. Okay. So then to get the active thrust or the total thrust for this single uh, layer of soil, so we need to count for this area. Okay. So for this area is half because it is a triangle shape times h height, then times unit width times height times Ka. Okay. So we simplify it into half h square gamma and then Ke. Okay. So then we obtain the same. Okay. So this is only can be used if we deal with a single type of soil. Okay. Multi-layer of soil, we cannot use this approach. Okay. So we need to count based on the C and phi, then plot what we call as the distribution diagram, and then get what we call as the area for each diagram. Okay, since the to move to the right away from the backfield, it means the system is an active state. According to column theory, the active thrust is expressed as Kpa is equal to half gamma h square Ka. Okay. Okay, then use these equations, okay, to get the Ka. Okay, as I mentioned, the equation includes the beta is the beta angle of the sheet of the retaining wall. Okay. It is not a 90 degree. Although it's 90 degree, we also need to put as 90 for the beta. Okay. Then we have phi. Okay. Delta. Delta is the internal the friction between wall and the soil. For this case, delta is count as 2/3 of the. So the phi for this case is equal to 30. Okay. So then calculate the value for this KA, okay. So alpha is the angle of the slope. So this is alpha. Okay. The alpha is the angle of the slope. Okay. So could you use your calculator? Try to get the KE. Is it same with the one that appear in this example calculator? Okay, because during your final or during your exam, okay, you need to do some calculations. So you need to familiar with the equations. Okay, try to calculate. Okay, I give you it should be only 1 minute. Okay, calculate first. That do you get the same value or not? Okay, calculate and let me know. Okay, you may separate. Okay, so this is will be the first value, the first sub equation, second sub equation, and the third sub equation. Okay, so the property, for example, alpha is 10, beta is 75, delta is 2/3 from 30, so 2/3 from 30 is 20. Okay, and the phi is 30. Okay, so the phi is different in terms of the symbol. Usually the phi is described based on this one, like this, not like this. Okay, so do you get same value? 0.67, 0.607. Dapat? Kena buat. You need to try. Make sure that you have calculator. Okay, so beta of 75. So it's so 75 plus 10, plus 30, hundreds. Okay, see. So 0.93. Then for the sub equations, beta 75 minus delta 20, 755. Sin 55 beta 75. Six, two, six. Then square root. Sin 30 plus 20, 50. Since sin 50 since 30 minus 10, 20 over since 75 minus 20. Dapat? Okay. Let me try first. 25 since alpha plus beta 85. Okay, then square root 1 plus, okay, then power by 2, 231, 2.31. Okay, so then what is the KA? 0.933 divided with 0.67, 626, 2.32. Oh, I obtained 0.642. I tak sama. Let me check first. 75 plus 20. Oh, okay. Wait. Sin 85 is 85. Wait. 75 plus. Okay, now is 0.93, correct? Okay. Beta. Okay, this is correct. 626. The last one. Since fifty, sin 20, since beta 75 minus 55, since 75 minus 75 minus 75, 45. The last one, since 10 plus 55, 2 plus 75, square root 1 plus power by 2. Okay, 295. Okay, this is 2, 9. Okay, then 0.93 divided with 57. Sorry, mistake on the 2.95. You obtain 1.56. 1.56. 2.45. Okay, 2.45. Okay. So I obtain 2.59. Okay, then you obtain 0.607. Okay, let me check again for the last one, for the 2.95. Sin P30 plus 50. 30 plus 20. So 50. sin 20 minus 10 divide with sin beta 75 minus 75 minus 20, 55. Sin alpha 10 times beta 85. Square root 1 plus answer power by 2. 197. Okay, 197. Oh, sorry. Dapat. Okay, okay. So I make mistake on this part. Okay. So then 0.607, 0.607. I'm not sure why I not get 0.607. So the first one is correct, second, and but the third is the third. Try again last for the last one. Sin 520 plus 30 plus 2050. Sin 530 minus 10, 20, 30 minus 10, 20, divide with sin 75 minus 20, 55. Okay, sin 10 plus 75, 85. Square root 1 plus. Okay, then I get the same. Okay, 2.45. 2.45. 45. So 0.93 divide with 626 times 2.45. So 0.608. Okay. Okay. So that is for the KA. Then later on, we get the PA half times 17 times 5 square times KA. So that is for the PA. Okay. So the total, the active thrust PA active at half, at 1/3 of the height of the wall, which is 167. Measure from the base of the wall at an angle of 35 with respect to the horizontal plane. So this thrust should be broken into its horizontal and vertical components. Okay. So how they did obtain 35? Okay, let me show it to you how they obtain 35. Okay. Okay. So this is the wall, and we need to draw okay, so we need to draw a normal axis. Okay, so then actually the what we call is the load is acting similar to the delta. Okay, so the delta is equal to 20 Okay. Because it is 2/3 from the fee. Okay. So now when we want to get what is the actual force acting in the vertical and also in the horizontal. Okay. Okay. So how to get the how they obtain the 35 angle. Okay. So this is 90 degree. Okay. Okay, 90 degree. Okay. Okay. So we need to the vertical force, okay, will be acting uh vertically, sorry, the horizontal force will be acting based on the uh x axis, and the vertical force will be acting at the y actual will be original y axis. Okay. So since it is a 90 degree, okay, so then we have what we call as a better angle of 75. Okay. So from here, this also should be 75. Okay. So means that we need to know what is the remaining angle of this one. Okay. So 90 minus with 75. So it is equivalent to 15. Okay. So the 15 plus 20, okay, is the angle that we use later on to get the y or the vertical and also the horizontal force at the actual uh, x and y axis. Okay, so 50 plus 20, okay, so is the value of the angle. Okay, that's why we use the angle of 35, okay, for horizontal, multiply with the cos or cos 35. Okay? So 129 is the value of the force or the value of the load. Okay? So then for the PAV, we use the sign, okay, to resolve the horizontal and vertical components. Okay, any questions? Okay, before we move to the next discussion. Okay. Okay, so then we have complete 5 examples, including two previous examples, so 7 to. So then I stop this example before we go for the next discussion. Okay, wait. Okay, wait. Hmm. Okay, we go for the example of slide number 59. Give it a minute. I need to take a drink. Give me 2 minutes. Okay. So, okay, based on our previous discussion, okay, so we deal with a problem, okay, uh, we assume first the wall is smooth, okay, second there is no better angle, okay, so this is the better angle. Okay, in this case we use we use the angle at the top. Okay, the third one, okay, if there is a slope on the top of the backfill. Okay, so I only at the moment I only able to show the full derivation. Okay, um, for the drain. Sorry, for the let me look first for the undrained. Okay, for the undrained case. Okay. Meanwhile, for the undrained case, we assume the wall is rough. Okay. Meanwhile, for the drain case, okay. So I will share with you later on. Okay. The full derivation. I mean the explanations. Okay. But in this slide, okay, we will go it based on what has been written in the slide. Okay. Okay. So there is a stress discontinuity, okay, approach, okay, because due to the wall is rough. Okay, so the planes or the stress plane or the principal stress plane will move. Okay, as shown in this diagram. Okay, so this happened due to the situations where the principal plane cannot have any shear stress. Okay? So in that case, they need to rotate. Okay, so it deal with the stress discontinuity conditions. So we look on the first slide, okay, to show on how the principal plane change, okay, and then we divide into two zone, okay. So we have zone 1. Let me enlarge it. Okay, and then we have zone 2. Okay, so the changes, okay, from zone 1 to zone 2, okay, is due to the frictional stress discontinuities. Okay, so basically this approach has been used for the shallow foundations. Okay, perhaps next week, okay, we will discuss on the shallow foundation, okay, issue. So in most practical cases, the wall will not be smooth, such that the may be generated along the soil wall interface. Okay, so because the wall is rough, okay, then there is the shear stress generated on the soil wall interface. So there will be a rotations of the shear plane, okay, which may also not be vertical, okay, but slope at the angle of W to the vertical. Okay, so it means that it is not be construct in 90 degree for the wall. Okay. If the wall is rough, then the principal stress will rotate due to the additional shear. So at failure, the soil in zone 2 on the active side will tend to settle and move towards the wall. The statement plus is actually it combine between it start to settle going down, but at the same time it move toward the wall. Okay. While the soil on the passive side, okay, will move upward and to the left because the wall push it. Okay. Stress generated as shown in figure in zone 2 on the active and passive sides. Okay. So this is the shear stress, okay, due to the effect of the wall roughness. Okay. So there will be two values based on the different soil behavior. Okay. For the under case, the tau W is equal to alpha Cu. Okay. And usually the alpha is reached between 0 to 1. Okay. And it should less than the value of the Cu, okay, when we multiply the alpha with the Cu. Okay. For the drain case, a, a, a difference where the sigma times with the tangent delta. Okay, so on previous example, okay, we can use the delta is equal to 2/3 of the phi because the delta should less than the phi. Okay, so we can use of the phi for the okay. So if we have tau w, means that the conditions of the principal plane is no longer valid in zone 2 in both the passive and active. Okay, so it means that in this case, we will have two more column circle with a different principal planes. Okay, directions. So the principal stress rotate through a series of frictional stress by as much as called as theta fan. Okay, that is for how they explain okay why the principal plane change. Okay, it is due to the roughness of the wall. Okay, and at the same time, if there is a angle of W, it also contribute to the changes of the principal plane. Okay. Okay, effect of the wall properties, roughness and the better angle. Okay, this is for the undrained case. Okay, so this is based on the more column or more circle diagram. So we translate it into what we call as the actual movements. Okay? So anything that change from more or anything that we use in the more column, we should divide it into two, as I mentioned before. Okay. So we have a major principal plane. Okay, so this is the tau. So where's the pen? Okay. So this is the tau. Okay, here. Okay. So then we try to illustrate the major principal plane for the zone number 1 here and zone number 2 on the next side. Okay. So before we discuss on this diagram, okay, we should look on the more circle diagram. Okay. So this is explanations on the more circle diagrams. Okay. So definitely the zone 2 is higher due to the depth is larger compared to the zone number 1. Okay. So before we calculate how much theta fan is, we need to determine how to relate the stress change when the principal stresses rotate from zone 1 to 2 to the soil parameter, C and phi, C or phi, and a general theta fence. Okay. So in this more column circle, okay, we could not determine the theta fan. That's why we translate it into the first diagrams. Okay. So the intersection between this area, okay, this area is considered as the position of discontinuity since sigma and tau are the same for both sides. Okay. Then S1 is considered as a zone 1. Okay. S2 is considered as a zone 2. Okay. Where the sigma 1, which is the maximum effective vertical stress, okay, is sigma 1 for zone 1 is located at A, and same goes to the sigma 1 for zone 2, where the maximum is at the edge of the column or more circle number 2. Okay. Okay. So since the position of the discontinuity of is located between the intersection between S1 and S2, so the tau, okay, is located at the intersection value line. It less than maximum CU value. Okay, so that is the alpha there. Okay, in order to guess or estimate what is the tau value. Okay, so it's more or usually it should be less than the CU. Okay. First, we consider the undrained case. Let's consider the principal stress rotations across discontinuity first. Okay? So we need to figure out by how much the major principal plane from zone 1 rotates into zone 2. Okay. So the condition of equilibrium has required both sigma and tau must be same on both sides, zone 1 and zone 2 of the discontinuity. Okay, as I mentioned, okay, so this is the equilibrium, okay, between the zone 1 and the zone 2. Okay, so the discontinuity will mobilize a shear stress which is less than the CU. So the more circle for stress condition in zone 1 and zone 2, assuming that the average stress increase from zone 1 and zone 2. Okay. To begin with, based on this diagram, okay, then we form a point A, B, C to represent the angle. So that is for the A. Okay, then look at the S. Okay, from there you get the angle, the rim on the other sides. Okay, okay, based on the full, based on the 180 degree, okay, is equivalent to the pi. Okay, that the remaining angle is pi minus with the delta. Okay. Okay, the position of the stress discontinuity is delta counterclockwise from the major planes of zone 1 in the more column circle. This means that in figure 3, okay, as I mentioned before, anything in more column circle, we need to divide it into 2 to be translated into the actual normal diagrams. So look again on the figure 3. Okay? The discontinuity, okay, is delta over 2 clockwise from the major planes of zone 1. Okay, so means that this is the major plane, so it is delta over 2 towards what we call as the discontinuity, okay, lines. Okay. So that is the delta over 2. Okay. So the position of the frictional discontinuity can also be established from the major principal plane in zone 2, which is pi minus delta clockwise, okay, here. Okay. This can also mean that the discontinuity is pi minus delta over 2 clockwise from the major principal plane of zone 2. Okay. From the 2, this angle is pi minus delta over 2. Okay. So we have pi over 2 and then pi delta over 2, then pi minus delta over 2. What is delta here? Is minus delta 2 minus delta. So pi minus delta over 2 minus delta over 2. So that pi pi over 2 minus, we can get the theta. So theta equal to theta. Okay. It share the same angle between this side and the next side. Okay. So the angle rotation theta of the magic principal plane from zone 1 to zone 2, okay, is theta equal to pi over 2 minus delta Q. So the increase of average total stress from S1 to S2, okay, is equal to Cu cos delta. So okay, how we obtain the 2 Cu cos delta? Okay. So we need to look on this angle. Okay. So is the distance between 2S1, S2 and S1. Okay. So then we need to use what we call as a trigonometry, because this is Cu. This is Cu. Okay. So that cos delta is equal to this distance. We put as an x, okay, x EU. Okay. So it means that x is equal to Cu cos delta. So then to get the distance between two S2 and S1, so it means that Cu cos delta we multiply with, okay? So then the distance is 2 Cu cos inside, put the theta inside the delta, okay? So based on these equations, okay, so the theta is equal to pi 2 plus with theta. Okay. Then put these equations to replace the delta in. So based on this approach, okay, later on we need to what we call simplify it, okay, to become as 2 Cu sines theta. Okay, so how to get 2 Cu sin theta? So we need to use the trigonometric identity in. Do you know how to use the trigonometric identity? Okay, let's see on the equation derivation. So be careful that I have changed the notation. Okay, you need to refer. Okay, you need to read the computer letter, because this is S2, not S1. Well, this is S1. Okay. How it works. Okay. trigonometry. Okay, so this is the trigonometry. Okay, so this is the so cos A plus minus B is equal to cos A cos B minus and plus sin A sin B. Okay, so for this case, it is a cos A minus B. Okay, so therefore cos pi over 2 minus theta is equal to cos A cos B plus sin A sin B. Okay, so cos pi over 2 theta plus sin pi over 2 sin theta. Okay, so cos 90 or cos pi over 2, because pi is 180 divided with 2, so it becomes 90. So cos 90 is equal to 0. Okay, and cos sin 90 is equal to 1. Okay, so then cos 90, okay, so this will be 0. This will be theta. Okay, so this will be 1. So at the end, the value is equal to sine theta. Okay, so we have proved that this 2cu cos pi over 2 minus theta is equal to 2cu sine theta. Okay. So then we prove that the 2cu sine theta. Okay. For super small increase in S1 to S2, okay, to occur at delta 90 and tau to Cu, okay. So S2 minus S1, okay, is equal to 2Cu sine delta theta, okay. So 2Cu d theta, okay, since sine delta theta is d theta because d theta is super small, okay. So later on the ds is equal to 2cu d theta, okay. So total rotation throughout a series of frictional discontinuity of total angle, okay, theta fan, okay, is integration of ds, okay, equal to 2cu integrations of d theta. Okay, so since the d theta is theta fan and 0, okay, so once we do the integration, so the 2cu is equal to 2cu theta fans. Okay. Okay, so that is for the how the derivation work, okay, to get the 2cu theta fan. Okay, so that is just for to get 2 cu theta fans. Okay, so yet what is the passive or active pressure, okay, to be used if we deal with this rough wall. Okay. 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 All right. Okay. I guess better for us to take a break. Okay. Uh, then we will continue back at 12:05. Okay. Okay, because this is too heavy. Eh? Okay. Okay, we take a break and we meet at 12:05. Eh? Okay.